Đúng rồi, chứ là
Can you hear me? Is it sound okay? I hear some echo. All right. There's some echo. It's very strange. Right. So during the lesson, if I accidentally mute my phone or you detect something unusual, please tell me immediately. Okay, if not, I just going on. Thanks, class. I'm going to share with you the screen. Let's play a warm-up game. Okay, play a covered game to review our previous lesson. Okay, I would love you to go to Kahoot using this link. I send you this link. Okay, and you put your name as you use your student ID. Okay, as the username. Okay, as your nickname. Use your student ID as your nickname for this game. Or you can use this Gambin. Everyone get it? Anyone got problem with logging the website? Let me know. Can everyone log in into the website, Kahoot game? Oh, I see. That's strange. Sorry, everyone. Let me check again. Last time it allows like 50 people, but why it's only 10 this time? Okay. Sorry. Let me check again. All right. In this case, we will play the live mode. Means I will open the game and then you will log in it. All right, I will ask the question and you will answer it in the live mode. So shall we try again with this game pin? I'm going to send you a new game pin. Okay. Can you log in into this game again with this game pin? I'm waiting for you log in and then we can start. It takes some time for all to log in. Seems that we have 32 players here. Right, I will start. We have 39 participations in the Zoom now. Shall I wait? All right, let's start. Input modeling refers to quantitative modeling or structural modeling or fitting a probability to data. Right. So, well, you can choose both the quantitative modeling and fitting probability to data. Both of them are correct, right? Because in input modeling, we have to deal with the data, right? So it's quite quantitative, okay? And of course, we also try to fit the probability to the data. So we have two correct answers here. Okay, very good. And all right, next question. Simulation speed of using random variate generation is faster than using input data directly. Is it true or false? Great. It's true, right? So one advantage that we fit in a probability distribution into our data instead of using it directly is the speed. Okay, so all right, so 2/3 of the class answer correctly. Well done. And let's try the next one. Fitting probability to data can generate variables that go beyond observed data. Okay, great. Okay, so it seems to be easy as well, right? That's right. When we fit the probability to data, the software like Arena will generate the random variables according to that probability distribution. Okay, and the number is generated is unlimited. But if we use data directly, we just use only the data that we input into the software, right? So this statement is also right. The way that Kahoot give the score to the player also based on the time to answer as well. So those who answer faster and correct will get higher score than the one who have the correct answer but slower. Right, so next. The shape of histogram is similar to the CDF, a PDF, a PMF. Uh, all right, so actually here we have two correct answers. It's either PDF or PMF. PDF is for the case of continuous data. We look at the probability density function. And PMF when we have the case of discrete data, right? So, but it's definitely not the CDF. The CDF is the cumulative. No, the histogram is similar to either the PDF or the PMF. Right? So we have two correct answers here, right? So it's good. Most of you can answer this question as well. Right, 18080, you regain your position. Okay, next one. Number of independent events occurring in a fixed amount of time follows which distribution? A number of independent events occurring in a fixed amount of time follows which distribution? Um, okay, half of us can answer this question. The answer is Poisson. Right, the hint here is we look at the number of independent events, right? So when we say the number, we can count it. And in the four given distribution, we only have Poisson is the discrete one. Okay, and yes, it is the number, and the events are independent. All right, so the correct answer is Poisson. Let's say we look at the arrival process, and we count the number of arrival per period of time. Okay, so this statement is similar like that one. Right, so Poisson is the correct answer. It's the only discrete distribution in these four answers. Okay, good job. Next one. This picture likely shows which distribution? Okay. All right. So like 90% of us can answer this one. The key thing is the plot you see is the continuous one, and exponential is the continuous one. But Poisson is discrete. All right. So that's the features that distinguish exponential and Poisson. Well done. All right. Next one. This picture likely shows which distribution? All right, it becomes easy based on the previous question, right? So you see the discrete data there is this person. Yeah. But remember, both exponential and Poisson distribution, we need to use the average rate to as a parameters for calculating the probability. Okay, so both use lambda. Is the point that we usually confuse for these two distribution. All right, next one. Okay, 18128 is back with an answer straight of 3. Next, how many parameters estimation for Weibull distribution? The correct answer is 3. We have the shape parameters, the location parameter, and the scale parameters. However, people usually assume that the location parameter is 1, right? So they just look at the shape and the scale parameters. But actually, Weibull distribution has 3 parameters. Okay, congratulations to those who answered correctly. This is difficult one. All right, we already 2/3 of the game. Now let's try the rest 4 questions. 99.79 is the 33.33% quantile of this data set. Is it true or false? All right, to answer this question, you have to be quick, right? You have to calculate the cumulative probability. We use the equation j minus 0.5 divided by n to calculate the probability. Okay, so it's around 33.33%. Okay, so the answer is correct. Okay, well done. Next one. The QQ plot indicates that the sample distribution is left skewed. Is it true or false? All right, this is a tough question. I didn't teach you this in class, but I give you the slide. Well, my point is just want to remind you that there are a lot of information that we can extract from the QQ plot besides concluding whether our distribution hypothesis is correct or not, right? And one of them is to see the shape of our distribution, whether it's the left skew or right skew. I guess that you give me a random answer, and that's why we have a quite random result here, like 50%. Right, but that's okay. That's okay. It's just a tough question. I just want to remind you for that point. Right, next one. A data set with 10 intervals is tested for triangular distribution. The DOF of the chi-square is? Whoa, we only have 13 correct answers. Right, let's recall if you chi-square test. And when we need to look for the radical chi value, right? And when we look at the chi-square table, distribution table, we need to know what is the radical what is the alpha value and what is the degree of freedom to check for the radical value. And the degree of freedom in the chi-square test is equal to k minus s minus 1. K is the number of interval, and s is the number of parameters of the distribution in our hypothesis. So here we have k is 10 intervals. We have 3 parameters in triangular distribution, right? So 10 minus 3 is 7, and then minus 1 is 6. So the answer is 6. Okay, remember this point. Chi-square test and the degree of freedom. Okay, we go to the last question. D equal to max fs minus sx is the test statistic of, I expect 100% correct answer for this one. Why there's still persistent 5 people who answer incorrectly? All right, this is the KS test, not chi-square test. All right, well done, class. So let's see the result of the whole test. All right, I will give the bonus score for the 3 winners here. Let me take note: 18242, 18080, and 18137. The rest who play the game also got 1 point bonus, but the 3 top winners will get 2 point bonus. Okay, this is bonus. Okay, well done, class. Okay, have to stop. Okay, we return to our Zoom screen. Is it? Mm, Okay, we go back to our lesson verification and validation. Okay, right, to recall what we have learned last week. The purpose of this lesson is to help us validate our model. That is to make sure our simulation model is the same, so-called, right? For sure, it's not exactly the same, but similar, okay, to the real system. And before go to the validation, of course, you have to verify your model. Okay, verification means make sure that your model um, has the logic in your conceptual model. All right, and the verification require you to practice a lot, right, in with the software. Okay, now for the validation, we are talking about the input-output transformation method. This is the only method that is objective. Okay. If we use other validation method, it's quite subjective because it's based on people opinion. But for the input-output transformation, is strictly based on statistical testing, based on the number. And the input-output here, in the input-output transformation method, we treat the system and our simulation model as a black box. What we care is the input and the output. Hold on, let me check this one. Okay, so for the input, we have uncontrolled variables, like the one we do the input modeling. They are random, and we have to identify their probability distribution. And we also have control decision variables. Now, for the output, we may also have many outputs in the system. But when we do validation, you only choose the most important input. Of course, the most important outputs, because the more outputs you want to validate, the more challenging. Okay. So just choose the key one that is important to your simulation objective. So last time we stopped here with the example of a bank management. Okay, so our primary output interest is the teller's utilization, the average delay or the waiting time of the customer, and the maximum queue length in the bank. So we will assume that the input is the same for both the simulation model and the real system. And now what we have to compare is to compare the output from our simulation model and the output from the real system. Okay. So this is our hypothesis. Our known hypothesis is the output. Let's say we are looking at the average delay from our simulation model. Okay, from our simulation model, the average output, we get the average delay. And let's say we go to the real system and we measure the delay in the real system, we get it 4.3 minutes. Okay, and from our simulation model, let's say we got 4 minutes. So we wonder whether 4 minutes from the simulation is the same with 4.3 minutes in the real bank or not. Okay. So last time I raised up that questions. How much difference between the model output and the real system is allowable? When we try to answer those questions, actually we have to think of what make it difference, what may make it difference. Okay, so of course, if our simulation model is not correct, the result is different. Now, but let's say if our simulation model is correct, can it still be different? Can be, right? And why? Right? If we think of our input variables, all of our input variable is random. Okay. So if you have a random input, of course, we expect a random output. So a random output here means that maybe with your simulation model, you run 20 times, you got the average from the simulation model is 4.1 minutes. If you run 50 times, you got the average from the simulation model is 4.8 minutes, and so on. Right? The average we get from the simulation model is also a random number. So even though if our simulation model is correct, the output still is random and is expected to be different with the real system. So the answer we want to reach is the difference significant statistical difference. Okay, we have the word here, significance. Okay, let me put it in the presenter view. Oh, this is not good. Okay, so we are talking about whether it is, hold on, I'm sorry. Okay, we are talking about whether the result here, okay, it is significant. And statistical difference. So the statistical here refers to the randomness nature of the event. We expect that it will be vary. It is a random value. We will get a value that is vary. But the difference here is it significant, right? So the hypothesis testing is trying to answer this question. Is it significant, statistically different or not? Okay. So firstly, we will try to answer this one. And later, we also think of another factor. Now, the result may be significant and statistical difference, but is it significant practical difference or not? Okay, so here we have two concepts here. One is statistical difference and another one is practical difference. Right. So let's say your simulation model give the average result is 5 minutes. Okay, 5 minutes. And let's say we do a hypothesis testing, and it say that yes, 5 minutes is statistically different with 4.3 minutes. It is significantly statistically different with 4.3 minutes. It's not the same, right? Now, but from the practical point of view, let's say if we if I have to wait for 4.3 minutes and they have to wait for 5 minutes, to me is the same. All right, so practically these two numbers is not significantly different to me. All right, so we have to distinguish these two difference. One is significant statistically difference, and another one is significant practically difference. Right, now we go for the first one first, the hypothesis testing, and we look at the statistical difference. Mm. All right, now, so we already learned, let me go to the table for this. Where is it? Hold on. All right, here we are. Okay, now, this is the result from 6 replication in our simulation model. Okay, we run the simulation for 6 times. In the run setup, we choose 6 replication. And let's look at the average delay. Okay, we look at this output average delay. This is the result from 6 replication in our simulation model. Okay, and we get the sample mean is 2.51 minutes, and the standard deviation from the 6 replication is 0.82. Right. So the question here is 0.51 minutes the same with 4.3 minutes that we measure from the real system? Right. Okay, we already learned the chi-square test and the KS test. Now this time we will use t-test to test for this hypothesis. Do you still remember t-test? This is kind of the most common test, the very fundamental one that we learn in the statistical course. Okay. So if we want to test the mean of a population, then we will use t-test. Right? So this is the sample from our population. Right? We want to test the mean. Is it equal to a certain number or not? Then we use t-test. Okay, we want to test the mean of a population, whether it is equal to certain value. Any hypothesis testing, we have a hypothesis, the null hypothesis, and the alternative hypothesis. And the second one, we have to compute the test statistic. So what is the test statistic in t-test? Test statistic in t-test. Okay, so you look at this one. This is a test statistic and t-test. Okay. So we will compare the average from our sample with the true value that we want to test. In this case, the average is 2.51 and the true value we want to test is 4.3. Okay. And we divide it by the standard deviation from our sample S. Okay. And divide it by the square root of the sample size. So we have 6 replication. We have 6 values here. Our sample size is 6. Okay, so this is our compute test statistics. It's the 5.24. Okay, so the third step would be comparing the test statistic with a critical value. So we need to look at the t distribution table and look for the critical value. So for t distribution, we have the degree of freedom. Okay. All right, recall that the degree of freedom in t distribution is equal to the sample size minus 1. We have 6 samples here. The degree of freedom would be 5 minus 1. Okay, and t-test is a two-tailed test. Okay, it's a two-tailed test. We are testing for the difference. So you would have 2 rejection regions, this one and this one. If you choose alpha equal to 0.05 or 5%, then each rejection region will be a half of the alpha. So this one would be 0.25 and this one would be 0.025. All right, half of the alpha. So in your t distribution table, you have to look for t alpha divided by 2 and the degree of freedom is n minus 1. Okay, this is a two-side test. Okay, we get 5.24 larger than 2.571. So you can think of this is our critical value, t alpha divided by 2. And our test statistic is larger than this one. This is our test statistic. It's 5 or something. It's found in the rejection region. Okay. Then our conclusion would be the output from our model 2.51 is different, is significantly statistically different with 4.3. All right. We already consider the randomness, right, from the statistical point of view, and we confirm that 2.41 is significant statistical difference with 4.3. Or the output from our model is different with the real system, and so our models is inadequate. It's not good enough. Right? Our model is not valid. We cannot use it yet. Right? So if our model is inadequate, what should we do? Let's say after hypothesis testing, we found that our models is inadequate. We have to reject our null hypothesis that the output from our simulation model is statistical similar to the real system. Then what should we do? Should we check our model in arena again? right. For this step, we no need to check the simulation model because we assume that we already do a proper job in verification. So the simulation model is really reflect the logic that we want. If any problem happen here, we have to check the logic that we assume, the conceptual one, right? So we have to check the logic that in our conceptual model, is it correct or not? Many times we make assumptions in that one, so we have to see whether that assumption is correct or not. And also we have to check the input data, right, to see whether our input modeling is it correct or not, or is there any problem with the data we collected, right? And then we have to calibrate again our model. Let's say we have to modify the logic, and then we modify the arena model, and then do the validation again, right? Okay, so for the next table, let's say we already revise the logic, right? We have made some wrong assumption and we fix it. So we run our simulation model again, and this time we also run 6 times, and this time get the sample mean is 4.78. Okay, so again we will conduct the hypothesis testing to see whether 4.78 is significantly statistically different with 4.3 or not. Right, and we have the new standard deviation here, so we will compute the new test statistic. All right. Okay, now we will talk a little bit again about the type 1 and type 2 error. Yeah, this one I already repeated many times in class. Right. For any hypothesis testing, we should be aware that there are always lying possible errors. Right? And we have two type errors here, type 1 error and type 2 error. Type 1 error is related to the alpha probability, and type 2 error related to the beta probability. So we have the null hypothesis. And the rejection region, alpha. Our null hypothesis would be the output from our simulation model is statistically the same with the system, or our model is valid. Okay, this one in short, it is valid. If our compute test statistic is here, is smaller than the critical value, then we have no evidence to reject this model. Right? We have no strong evidence to reject our model. Right? However, when we make that conclusion, we also know that we may commit certain error. We may not, we don't reject it, but there's a possibility that it's wrong. Okay, so type 1 error is the error of, type 2 error is the error of accepting the model that is invalid. Okay. We say that we don't reject, our model, we accept it. But what happens if our model is wrong and we still use it? Okay, that is the very serious problem, and it's sent to type 2 error. We accept a model as valid when it is invalid. But for type 1 error refer to you reject it. You reject it here, but it is a good one. You reject it. That one is not serious compared to you accept a wrong model one. So now we will focus on the type 2 error, right? The probability of commit type 2 error. The type 2 error, the probability that we commit type 2 error is beta, and it is related with the probability alpha as well as the sample size or the number of replication we run our simulation. Okay, and the sample size, the number of replication, alpha and beta has the relationship. So let's say if we fix the number of replication n and we increase alpha, then we will decrease beta. In other words, we have the trade-off between alpha and beta. Right. Naturally, we would like to have both alpha and beta small, right, because it's a probability of our error. But we have a trade-off here. We cannot have both of them small. So what is the appropriate value for the number of replication, alpha and beta here? Okay, so now I will tell you how to decide the number of replication so that we can get an acceptable probability type 2 error, beta, as well as alpha. Okay, we will try to determine this one so that we can have an acceptable value of alpha and beta. Okay. All right. Okay, related to the type 2 error beta, we have another ways to refer to it. It is the power of the test. The power of the test. The power of the test is the probability that we can detect an invalid model. Power of the test is the probability that we can detect an invalid model. So if beta is the probability that we cannot detect an invalid model, it's type 2 error, we fail to detect an invalid model, then the power of the test is equal to 1 minus beta. We are looking at able to detect an invalid model and unable to detect an invalid model. The sum of them is 1. So people can either refer to type 2 error, the probability of type 2 error beta, or refer to the power of the test. All right. So for determining the sample size n to get the acceptable probability, type 2 error or the power of the test, we need to use this so-called operating characteristic curve. You can find this curve in the appendix in your textbook. It's in the appendix, and it is table A10. Right. So how to use this plot? Right. So right on the y-axis here, the y-axis here is the probability of accepting our null hypothesis. And in this case, we are talking about an invalid model. We are accepting an invalid model. So the y-act is beta. It's the probability that we accept an invalid model. Okay, and this table, you can have different table for different alpha value. A standard value of alpha, we usually choose 0 0.05, 0 0.01, 0 0.025. Right? That is the common value of alpha, which is acceptable. So let's say if you choose alpha equal to 0 0.05, then you look for the OSIF. The OSIF means the operating characteristic curve for alpha equal to 0 0.05. Now the x-axis give us the value of delta. What is delta here? This is the delta. The delta here is defined as the true difference between the expected value from our simulation model and the real system. This is the expected one, okay, and this is the real system one, the true difference. So like what I mentioned before, this is refer to the practical difference that we expect between our model and the real system. So you may ask the manager of the system, what is the difference you expect between the simulation model and the real system? Okay, if he say that, well, I allow 5 minutes different from your simulation model and my system. If your simulation model give a result that about 5 minutes different with my system, I consider is the same. Larger than that, it is really different. Or the manager may say, well, I allow 15 minutes difference. To me, 15 minutes different is like smaller than 15 minutes is still it doesn't make any difference as long as, but if your simulation model give a result that is 50 minutes difference with my system, is really, I would consider it's really different. Okay, so that one is considered the practical difference, not the statistical one. Right, so you have to identify this one. This one is subjective, it's up to you, or it's up to the user of the system to determine this difference. Okay, and then uh, mu here, sorry, sigma here is the standard deviation from our samples, right? Like you run the our simulation SID replication, then you can identify the sigma. Okay. So you got this one, you divide by this one, you will get the value delta. And this is the delta in this plot. Okay. Is the ratio between the true difference that we expect between the simulation model and the real system, okay, over the standard deviation. All right, now take an example. Let's say we allow 1 minute difference between our simulation model and the real system. So as long as the difference is within 1 minute, we will consider it's the same. But if it's larger than 1 minute, then it is different, okay? And from our simulation result, like we run 6 times, for example, we get the standard deviation 1.66. So we will take these two ratio and we got our delta value is about 0.6. Right now I will looking for the delta about 0.6. 0.6 is around here. Okay, so what is the relationship between the number of publication and the value beta here? Let's say if you choose to run a simplification, just now the expected value you get here and the standard deviation you get here is from simplification. Then you look for n equal to 6. This is the number of replication that you run. All right, so 6 replication is somewhere between 5 and 7 here. All right, well, you can treat it as 7. You can imagine a curve between 7 and 5. Let's try number 7, which is close to number 6. Okay, so we put it here. Somewhere here. This 7, n equal to 7. And this is n equal to 5. So n equal to 6 is somewhere here. Okay, approximately, just approximately. So if it is around here, then our beta value would be around 0.8. Beta equal to 0.8 or 80%. Is it a high number or small number, class? Like 80% that we may commit type 2 error, or 80% we may accept an invalid model with simplification. So is 80% a high number or a small number? It's high, right? Okay, 80% that we can commit that error, that we accept an invalid model that is too high. Okay. So how can we improve this one? How can we reduce type 2 error? How can we reduce the value of beta? Or how can we increase the power of our text? We have to, okay, let's try. Now, by common sense, should we increase the number of replication or reduce the number of replication? Common sense, the more we run, like the easier we can detect whether our model is right or wrong, right? Okay, so let's see if we increase the number of replication. Yeah, that's right. Right, thanks Ngọc, you're right. Let's try increase the number of replication. Let's try increase by 15. Okay, increase by 15. So the same here, we have the same value of delta here. We assume that this number delta doesn't change. Of course, it will change. When you increase the number, you will have more samples. So the expected value here will change a little bit. Okay, and the standard deviation also change a little bit. All right, but because we physics here, we physics it. This is 1 minute. This is what we allow is 1 minute. So it doesn't change. But when you increase the number of replication, this one may change a little bit. But let's assume that delta doesn't change much. So we still physics here. Increase the number of replication to 15. It is here. 15 is here. then the beta can be reduced to less than 50%. That's good, but not good enough. Let's say I want to increase the power of the text to 10%, like sorry, to 90%, like 90%, I can detect an invalid model, or beta is just 10%. It's only 10% that I accept an invalid model. Let's try, I only want beta 10%. So I only want beta 10%. So how many replication I should run? Okay, it's around here. All right, it's around like 40 times. You need to run 40 times to reduce the probability of type 2 error to 10%. Okay, so wow, 40 replication or 50 replication or even 100 replication in simulation can be very fast, right, for most of the cases. So don't worry about the number of replication. But take note that when you use Arena, um, after you already do the verification, and you don't need to look at the animation anymore, you just want to increase the speed of the simulation because you have like 50 replication. Then you go to the run setup and choose the batch one. Choose the batch option. Okay, when you choose the batch option, uh, the software will run real fast because it will ignore the animation very fast. So you can get 40 duplication in a second. Right. But if you want to verify your model, you don't choose the past one so that you can still see the animation on the screen. You use the highlight active module to observe the flow, the entity, and that is slower. All right. Okay. Any questions so far? Okay. So in short, we need to usually we fix a value alpha. Okay. A standard alpha value is 0.05 or 0.01. And we usually fix that one. And to determine the number of replication we should run, right? So we can get an acceptable value of beta, and you can use the OC curve to determine the number of replication. From the number of replication, after you have n, okay, you also can use the hypothesis testing, the t-test, right? This t-test, right, to see whether you to get conclusion whether our simulation model output is significantly statistically different with the system model. Okay, class. Let's see. Is there any question? Okay, if not, we stop here. We take a break. Okay, we take a 10 minutes break, and then we return. Okay, we take a break, everyone. Hi class, I'm back. Shall we start? Hello. Alright. Hi Sang. Hi Khanh. About others? Are you back? Okay, Phương. Alright, Win. Alright, let's continue the rest. Alright. So what we just talked is using the hypothesis testing to test the value from a specific value from our simulation model. Okay, and that one, because we use the average of the output from our simulation model, that one we call the point estimate. All right. Remember, we run our simulation models for many times, many replications. Each replication, we got the average, and then we take the average of many replications, and it gives us one average value. So we call that a point estimate. A point estimate. Sorry, point estimate. I'm sorry. I'm sorry. My child just called me. All right. But we have other ways to estimate the result, a statistical result. Instead of looking at point estimate by calculating the average, we can look at a range estimate. Okay, so that's when we calculate the confidence interval. Okay. Instead of saying the average waiting time is about 4.7 minutes, we can say the average waiting time is ranging from 4 minutes to 5 minutes with 95% confidence. In other words, like we have 95% confidence that our waiting time has a value from 4 minutes to 5 minutes. Like there are two ways to estimate a statistical value, a point estimate or an interval estimate. The hypothesis testing that we just conducted is looking at the point estimate, and we compare that point estimate with the real value from our system. Okay. Now let's say, how about if we want to look at the range estimate or the confidence interval from our simulation output? If you pay attention to your arena report, you see that it shows us the average value, the maximum value, the minimum value, and the half-width confidence. So what does it mean here? Okay, you look at this equation. This equation give us the confidence interval calculation for our simulation output. Okay, instead of looking at one point, looking at the average here, we want to know what is the range of our statistic with 95% confidence. Okay, so this gives us the range here. right? So we can say that let's say we're looking at the waiting time. The waiting time would ranging from the average minus t alpha over 2, all right, minus this one, right? This one we call half width of the confidence, all right, to y, the average plus this value, plus the alpha over 2, and so on. So this is half width. Okay. So you can imagine our confidence intervals like this one. This is our average. Okay, this is our average when we use the point estimate, and this is a confidence interval. Right. So 95% of the average will be within this interval. 95% we will find that our average value will fall within this interval. And this interval start with y minus t alpha over 2 multiply with s divided by square root of n. Okay, and the other end of the confidence interval is y plus t over alpha divided by 2 multiply with s divided by square root of n. Okay, so this one, the one that I'm circled here, we call this a half width confidence interval. Half width. This one is half width. All right, and from here to here will be the width of the confidence interval. Okay. Now we will try to validate our I/O input output translation by using the confidence interval testing instead of looking at the hypothesis testing with the point estimate. Where is it? Now, so firstly, let us look at the formula to calculate the confidence interval for our average value here. Do you have any comment with this one? Like, what is the relationship between the width of the confidence interval and our sample size? Right, we try to estimate the average value from our model. This is the average value, and we also can compute the confidence interval using this equation. Right. So what is the relationship between the width of this confidence interval with the sample size, or with the number of replication that we will carry out? Anyone can answer? What is the relationship between the sample size? Okay, this is the number of replication. Okay, this is the width of our confidence interval. What is the relationship, everyone? Reciprocal relationship. Okay, so it means that if we increase the number of replication, all right, if we increase the number of replication of the sample size, like we increase n, then the confidence interval will be small. That's right. Okay. You see here. Let's look at it again. Okay, we increase n here. If we increase n here, this one will become smaller because n is in the denomination, right? All right, so we increase the number of replication, then our width of confidence interval will be reduced. Now, what would you prefer? You prefer a small width of confidence interval, or you prefer a large width of confidence interval? Which one we would like to have? Like I say, 95% that the waiting time is from 4 minutes to 5 minutes, or you would prefer 95% that waiting time would be ranging from 1 minute to 10 minutes. Right. So the first one, 95%, the confidence interval of the waiting time is 4 minutes to 5 minutes. That is the very small confidence interval. The width is very small. Right. The later I say 95%, the confidence interval of our waiting time would be from 1 minute to 10 minutes. That's larger. Of course, we prefer the first one. The first one gives us more accurate result, right? Or I can say, well, 95% confidence that our final score would be from 20 points to 100 points. Right. Wow, that's no value to you because the range is too large. The estimation is too wide, right? So we prefer a small confidence interval, a small width of confidence interval. And if we want a small width of confidence interval, we need to have a high number of replication. Okay, so remember this principle, this basic relationship between the confidence interval and the sample size, or the number of replication in our case. Okay, now let's go to the next point, how to use the confidence interval to test, to validate our model. Here you have, say, we will have two situations here. Okay, now let's say this is our confidence interval. All right, so 95% the average output from our simulation model will ranging from here. Okay, follow me. This is our confidence interval. All right, this is the mean of the average. All right, and this is the average minus the half width. This is the average plus the half width. Now, the true value from our system in the first scenarios is falling outside our 95% confidence interval. It is here. So it is outside the confidence interval. Right. And the second scenario, this is our confidence interval. Right. This is somewhere. This is the mean here. Right. And in the second scenario, we have the true value from our system is fall within the confidence interval. Right. We are looking at these two scenarios. Right. Now let's look at for the first one. When we have the real value of our system, let's say the 4.3 minutes we say, is outside the confidence interval, what will be our conclusion? We calculate that 95% that our waiting time will fall from 2 minutes to 4 minutes. And then the real system give us the waiting time 4.7 minutes. Let's say this is 2 minutes to 4 minutes. This is the estimated confidence interval, and what we have is 4.7 minutes. What will be your conclusion? Is our model valid or not valid? Is it similar to the real system? Is the output from our model similar to the system? All right. It makes sense that you think it's invalid because, well, 95% the output our simulation model is here. All right. So the rest is only 5%, but and the real system is in. So it's very likely that we conclude that it's invalid. Right. However, let's think more carefully about this case. If we think of the practical difference, if what you want to consider the practical difference between our simulation model result and the system, what would happen? Just now, what we thought is just the statistical point of view. Right now, I want to involve the practical difference between the real system and the simulation model. How should we consider? Okay, so let's say I have an epsilon. Okay, epsilon would be the allowable difference between the simulation model and the real system. Like it's just like when we discuss about the probability of type 2 error. Okay, here we also can involve epsilon here. So we allow that epsilon to be 5 minutes, means as long as the simulation output and the real system is within 5 minutes difference, we would consider is the same from a practical point of view. Then what should be our conclusion? Right, and you look at here. Let's say we give epsilon equal to 5 minutes. And here it is 4 minutes, it's 4.7 minutes. It's like only 0.7 minutes different, but we allow 5 minutes difference. All right, so in this case, when we also consider the practical difference allowable between the simulation output and the real system, we will look at these cases. Okay. For the first one, let's say I will look at the difference. Let's say this is my confidence interval, right? The high end one, right? And this one and the real one here, I will call this one the best case scenarios, the best case one. Why call this best case? Because when my simulation output is here, the difference between my simulation output and the real system is the smallest one, right? It's the smallest compared with other values. So this one I say this is the best case I have when my simulation output fall in here. Let me delete it. The drawing start to be messy. Let's try again. All right, so when my simulation output is here, this is the best case I have because the difference between the simulation and the real system is the smallest compared to other case. Now, when my simulation output fall in this at this point, at the end of the confidence interval, I call that this one is the worst case because the difference between the simulation and the real system in that case the largest. All right, and I know this value. I can compute this one. I can compute this one, and I know this one. Okay. Now, case number one. If the best case error, the error is the difference between the simulation and the real system is the best case error is larger than the epsilon allowable. What should I conclude? Let's say I allow epsilon is 5 minutes and my best case error is larger than the allowable 5 minutes. Is my model valid or invalid? Reject the model. Why? Phương, can you explain why you should reject the model or why is this invalid? Right, the best case is the smallest error that we have, right? If the best case larger than S0, then for sure other cases also larger than S0. Right, that's right. You give the correct answer, Phương. The best case, the smallest error we have is already larger than 5 minutes. Then for sure the other case that we have here, including the worst case, will be larger than S0. Right, this is the allowable value. 5 minutes is allowable. So, so we should refine our model. Okay, so our model needs to be refined. It is invalid. We have to calibrate it again. We have to refine it again. All right, so that is case number one. Now, case number two. If the worst case error is smaller than epsilon, if the worst case error is smaller than epsilon, what should we conclude about our model? The worst case, the worst case error is smaller than epsilon. Think carefully. When the worst case error, the difference, the largest difference, the largest possible difference between our value epsilon. What should we conclude about our model? Is it valid or invalid? Hello? All right, standing up. It's valid, okay. The worst case error is that the largest difference, the largest possible difference between our simulation and the real system, but it's still smaller than epsilon, it means that the other value is also smaller than epsilon, right? From here to here is smaller than epsilon, so the other value in the confidence interval should be smaller than epsilon. So the difference always within 5 minutes. And so we will accept the model. Our model is considered valid. All right, now we have the third case. We done here. The, for the second one, we accept the model. Now the third one, if our best case error is smaller than epsilon, let me delete this one. Now, is our best case error smaller than epsilon? But the worst case is larger than epsilon. What is your conclusion? Right, so we have epsilon here. Okay, our best case is this here. This is our best case error. And this is our worst case errors. What is your conclusion? It means that if our simulation model output phone here is smaller than epsilon, means that it's okay. The difference is okay. It's smaller than 5 minutes. It's okay. Our model is okay. It's valid. But if the simulation model, the simulation result is here, in the worst case, it's larger than epsilon, then it's not good. But we don't know where it's formed. We just know that 95% is ranging from here to here. What is your conclusion then? The conclusion would be there's no conclusion. All right, we cannot conclude anything here. We couldn't reject our model. We cannot say it's invalid, but we also cannot say it's valid, right? Because we're not so sure. The simulation are ranging from here to here. 95% is here from here. All right, and there's a case we accept. There's a case we reject. Right. But because we cannot get any conclusion here, what we can do is we would run more replication. And how running more replication help us to get to the conclusion? The advice is you should run more replication. But how running more replication would help? You remember this one? When you run more replication, you will be able to reduce the width of the confidence interval. Right? You will be able to get a more precise prediction of the confidence interval. So let's say if you run more replication, right? The width of the confidence interval will reduce. You will be able to predict more accurate. So let's say it reduce like this one, it reduce. Okay, from here, all right, to here is reduced. So when you reduce the confidence interval width, all right, you see what you see here. You see the best case tend to increase, right? The best case tend to increase. the best case tend to increase. Now, it can increase to a certain, there may be a time where it can increase to certain value that you can get. It's higher than epsilon. And then you can conclude that your model is invalid. Or if it is a worst case here, you will see the worst case reduced. The worst case reduced. And it may reach to a certain point where it reduced to a value that you see that is smaller than epsilon, and you see that your model is valid. You can conclude that your model is valid. Right. So by reducing the width of the confidence interval by running more verification, we may able to reach either this conclusion or this conclusion. Right. If your confidence interval is too wide, if your confidence is too wide, the best error is very small and the worst error is very large, then you cannot conclude anything. This is the third case, you cannot conclude anything. Right? So more verification make the confidence width small so that you can reach to either rejection or accepting your model. Okay, if you have a very wide estimation, it will be no use. That's the point. All right. Now we try for the next one. The next one, this is our confidence interval. All right, and the true value, the value of our system fall within the confidence interval. So by common sense, from the statistical point of view, we may say that our model is valid, right? Right, because the real system falls within our 95% confidence interval. But let's say if we also want to consider the epsilon one, would the conclusion be different or not? Right, now we consider our epsilon. And again, we also have the best case and worst case error. Right. Let's say if we define the difference between between the real system value, this is the real system value, and the closest distance between the real system value and the end of the confidence interval, right? From here to here, the smallest one is the best case, and the difference, the largest difference between the real system and the other end of the confidence interval is the worst case. Right. Then we also can argue similarly like what we have done right now. So let's look at the next one. When we have the best case larger than epsilon, what is our conclusion? Our best case larger than epsilon. Larger than epsilon means it's good. Okay, it's not good. Larger than the allowable value is not good. So should we reject our model? Should we say that it is invalid? Like this one? Like this one, we have the best case larger than epsilon. Then we conclude that our model is invalid and we need to refine it. Is it the same here, class? Is B the same with A? You look at situation A. In A, we have the best case larger than epsilon is guaranteed that the other cases here on the value in the confidence interval here, right, from here to here is also larger than epsilon. However, in situation B, we have the best case larger than epsilon. It doesn't guarantee that other cases also larger than epsilon. So if our value is here, it's not at the end of the interval here, but it is here. So the error is just from here to here. It's not necessarily larger than epsilon. So we still have cases that's smaller than the best case. It is here. All right, it's smaller than the best case and it doesn't guarantee it's larger than epsilon. Or it is here. From here to here may be smaller than the best case. So in brief, even though we have the best case larger than epsilon, there's still other values in the confidence intervals may not larger than epsilon. So we cannot say that we totally reject our model in this case. So again, we have no conclusion here. And what we can do is run more replication unnecessary, right, to get to say that our model is valid or invalid, right? Similarly, if we have the worst case larger than epsilon, the worst case larger than epsilon, what will happen, class? We have the worst case larger than epsilon. It's still the same. The worst case larger than epsilon doesn't mean that other cases, right, fall within our confidence interval larger than epsilon. All right, we still have other cases, and it's not necessary that it's larger than epsilon. So we cannot say that we reject our model at this point. We still need to run more replication to get the conclusion of refine our model or accept our model. Right. So in short, best case or worst case error larger than epsilon, more replication are necessary to get to the conclusion. Okay, the last one, if the worst case error is smaller than epsilon, the worst case smaller than epsilon. What is our conclusion? Now you can answer this one. If the worst case smaller than epsilon, you can answer this one. You need to think, if the worst case smaller than epsilon, does it guarantee that other cases also smaller than epsilon or not? If other cases that fall within the confidence interval also smaller than epsilon, then we accept the model. That's right, T. Okay, now we look at here. Our worst case is the largest difference, the largest possible difference with the real system. Okay, and it's smaller than epsilon, so other case would be also smaller than epsilon. So in this case, we would accept our model. All right. Right. So all of these then list all the possible scenario that we may have. You can well after this lesson, when you review the lesson, you can spend time and think about it. Does it cover all the situation? Actually, it did. Alright. So okay, let me summarize again. Right, we will have case where our confidence interval okay, the confidence interval does not contain the real value of the system, like this one. In this case, if the best case error larger than epsilon, larger means not good, okay, larger than the allowable value is not good, then the model needs to be refined. Our model is invalid. We need to refine. We need to check the logic. We need to check the data input, refine it until it's, we get a valid one. If the worst case error is smaller than epsilon, we can accept the model. The worst case error in this case, smaller than epsilon, would guarantee all other cases that form in our confidence interval smaller than epsilon, so we accept, right? And we have the third case, when the best case error is smaller than epsilon, but the worst case is larger than epsilon, right? In this case, what happened is our confidence interval is too wide. The best case is very small and it's always smaller than this one, and the worst case is very large and it's always larger than this one. The confidence interval is too wide. We cannot get any conclusion. So more replication are necessary to narrow down, to reduce the width of our confidence interval, so that we can either get to this conclusion, accept, or refine our model. Okay, and then we have the second scenario where our confidence interval contain the true value of the system. All right, in this scenario, either the best case or the worst case error is larger than epsilon, we still need to run more replication in order to be able to conclude whether we need to refine our model or accept our model. All right, and the last one is the worst case smaller than epsilon. So this one is the same with here. These two is the same. We will accept the model. So, well, let's say in your project, when you do the validation, you can choose either. You can choose either method. You can choose using hypothesis testing, look at the point estimate, or you can choose the confidence intervals testing like this one to see whether you accept or need to refine your model. Okay, you can choose either options. All right, let's try, let's take an example and then we stop. Okay, so let's say here I have in our bank example, the waiting time from the bank. This is the real waiting time from the bank is 4.3 minutes. And let's say the bank manager say that a close enough is 1 minute. So it's he allow the difference between our model and his bank is 1 minute. More than that, he will say our simulation model is not good. But the difference is within 1 minute, he will say, wow, I can use your model, right? And then we run our simulation, we get the 95% confidence interval from our certification in simulation is 1.65 to 3.37. Can you tell me what is your conclusion? Okay, you can plot 1.65. You have 1.65. This is our 95% confidence interval to 3.37 minutes. 95%, the average waiting time from our simulation would have this value from 1.65 to 3.37. Okay, our real system is 4.3 minutes. All right, I got one answer here from Min. More replications are necessary. Do you agree? Alright, so this is a case where we have the real value is outside the confidence interval. So this will be our best case, and this will be our worst case. And in this case, our worst case is 2.65. Right, and it's larger than x0. Our worst case is larger than x0. But our best case, let's look at our best case. Our best case is the difference from 3.37 to 4.3. It is smaller than x0. All right, our confidence interval is too wide. The best case is very small, and the worst case is very large. It's too wide. We have to run more replication, right, to narrow down the confidence interval width, and then we will be able to say whether we reject or accept this model. Okay, well done, class. All right, so it's good. You get it? All right. We let's say, what time is it now? Should we stop here? Should we continue? Let me check the time. What time is it? Oh, we are almost run out of time. It's 4 o'clock. Maybe I speak too slow. All right, so we stop here, and we very likely 95% that we will continue online class next week. For those who study the lab, we will have the lab on Wednesday and Friday, right? Actually, what we are going to do is like this one. I just make you very brief online for the lab lesson tomorrow. We start at 1:15, like 1:15 p.m. on Wednesday, and let's start 8:15 on Friday. I just give you a very brief like what you need to do, and I give you the exercise. All right, so I give you exercise at home, all right, and you will do it on yourself at home. We won't stay like the real lab one, and the deadline for it will be 2 weeks. So after 2 weeks, we will see how the situation go on. Okay, if it's better, then we can have the offline class, the last offline class, where I can give you the answers for all your questions, and also teach you some important point how to deal with the big data for the last case problem. We need to do certain programming, example, integrate into our simulation. Okay, but basically for this week, for the lab, we just meet very briefly. I will brief you what you need to do for the exercise at home, and you have 2 weeks to do it on your own. Okay, all right, so do not be late, because when you show up late, then we are already up, right? If you attend the lab tomorrow or Friday. Okay, now last one, I would like to check the attendance of these people. Sơn Tùng, are you here? Sơn Tùng. Sơn Tùng, are you here? Hello, Sơn Tùng, are you here? All right, I saw you on the screen, but you didn't respond to me, so I don't think that is a valid a valid attendance. Okay, Sơn Tùng, are you here? No, not. Nhung, are you here?
Yes.
Okay, Nhung. Good. Do you have any question today, Nhung?
Yeah. No, teacher. But is that my name?
Yes, I think so.
Yeah. Okay. Thank you.
You asked me thì Hồng Nhung, right? That's
Yeah.
right.
Yeah.
Okay, Nhung. Good. Giang Nghi, are you here? Giang Nghi. Giang Nghi, are you here? Hello, Giang Nghi. All right, Giang Nghi absent, right? Okay, let me see. Lucelle. Thanh Hương, are you here?
Dạ có cô.
Thanh Hương, rồi. Thanh Hương, hôm nay có câu hỏi gì không em? Có
Không cô.
Không. Ok. Rồi cô hỏi còn bạn Mạnh Tiến có đây không em? Mạnh Tiến. Hello Mạnh Tiến. Rồi. Mạnh Tiến không có ở đây ha. Rồi. Ok, vậy mình ngưng tại đây ha. Các bạn sau đây là cô muốn ở lại nói chuyện với cô một chút nha. Các bạn mà vừa rồi cô mới gọi điểm danh á, Thanh Hương nè, Giang Nghi nè, Hồng Nhung nè, Mạnh Tiến, Sơn Tùng nè, các bạn ở lại nói chuyện với cô chút nha. Rồi các bạn khác thì có thể ốp được rồi.